Okay, in this video, we're going to talk about absorbing Markov chains. So this is a special type of Markov chain where the behavior is a little bit more interesting, where the steady state matrix starts to get more entertaining, and where we have to interpret things in a slightly different way. Okay, so what an absorbing Markov chain is it's absorbing Markov chain has at least one absorbing state and an absorbing state is exactly what it sounds like. It's a state that keeps everything in it. It collects all of the different values in it. So in terms of our state diagram, the state where the only arrow out goes back to itself with weight 1. Right? So all of the arrows out of a particular state have to add up to 1. And so if there's only one arrow going out, it has to have weight 1. And that one is going to go back to the state itself. Okay? So for example, I'm going to make x sub 3 here an absorbing state. And I do that just by drawing one arrow and labeling with weight 1. Okay? Now you will still have arrows going into x sub 3 from the other states. So for example, you might have 0.4, 0.3, something like that. 0.1, 0.2, 0.4, and then from this one, 0.6. Okay? So all of this still adds up to 1, all the arrows going out, 0.1 plus 0.6 plus 0.3, it's still a Markov chain. X sub 3 just has this one arrow going out. It doesn't have anything going to x2 or x1. And so what's going to happen with that is all of our values are going to end up in x sub 3. Okay? So that's why it's called an absorbing state. It absorbs everything. And so eventually your steady state is going to be 100% of the values end up in x sub 3. Okay? And so if you look at setting this up, right, you've got x sub n equals, what's our matrix? X sub 1 is 0.6, 0.2, 0. X sub 2 is 0.1, 0.4, 0. And then x sub 3 is 0.3, 0.4, 1. So our matrix A looks like this. Okay? And if you take a power of this matrix A, if you say take A to the 100 power to get your steady state matrix, that steady state matrix is going to look like this. 0, 0, 0, 0, 0, 0, 1, 1, 1. Everything ends up in state 3. Okay? So 100% of all the values end up in state 3. Okay? And so the dominant eigenvalue here is 1. The dominant eigenvector is 0, 0, 1. 100% in state 3. So this isn't actually any different than what we did before, except everything ends up in that absorbing state. And I'll have an Excel simulation of one of these in the file that's attached to all of this as well. What's more interesting is when we have multiple absorbing states. Okay? So if we have a situation where there's more than one absorbing state, this actually gets to be a lot more interesting. Okay? So I'm not going to draw up the state diagram. I'm just going to give you the matrix A. So let me give you the matrix. I'll point out kind of where you can see, just like here, there's an absorbing state because there's a 1. you're going to see it in the matrix for this, that there are two absorbing states. Okay? And then we'll talk about the steady state matrix. So consider a Markov chain with matrix A equal to 0.3, 0.4, 0, 0. So 4 states now rather than 3. 0.2, 0.1, 0, 0, 0.5, 0.2, 1, 0, and 0, 0.3, 0, 1. Okay? So you can see here x sub 3 and x sub 4 are both absorbing states. So they absorb the values. Everything is going to end up in x sub 3 or x sub 4. And so what's interesting, the question becomes, what percentage ends up in x sub 3 and in x sub 4? And that actually has a really interesting answer. Okay? So if you actually do this, so we can look at our steady state matrix. So if you take a to the 100, you take a power of this, what you're going to see is your steady state matrix looks like this. 0, 0, 0, 0. Nothing ends up in state 1. Nothing ends up in state 2. Okay? But where it gets interesting is the rest of the matrix. So 0.89, 0.62, 1, 0, 0.11, 0.38, 0, 1. Okay? So what you see here is that you've got two. This isn't like our steady state matrices before where everything is cut and dry, right? Everything ends up in state 3. Now something more interesting is going on. The way that we interpret this, because if you think about this steady state matrix being applied to your initial value, right? So remember when we thought about this, our model was that x sub n was this a to the n times x sub 0 times our initial conditions. So what this means, since this is getting multiplied by our initial conditions, what it means is that 89% of what starts in x1 ends up in x3, and 11% ends up in x4. So 89% coming from this number ends up in x3. 11% of what starts in x1 ends up in x4. Okay? Similarly, 62% of what starts in x2 ends up in x3. 38% of what starts in x2 ends up in x4. Okay? So if you had a situation where, say, you started with, say, your initial values, you started with 100% in x1. So everything, your entire population, whatever it is that this model is representing, starts in x1, you would end up with a steady state where 89% is in x3 and 11% is in x4. If you started with everything in state 2, you would end up with 62% in state 3 and 38% in state 4. Now, if you started with some mix, it gets more complicated, right? So if you started with 50% in x1 and 50% in x2, you'd have some combination of these. 0.5 times 0.89 plus 0.5 times 0.62. 0.5 times 0.11 plus 0.5 times 0.38. Okay? So we'll do an example like this. We'll actually work through a real example and see kind of how we can work with these Markov chains in the next video.